is a solution to question 5 on the Physics 211 practice exam. So this references the demo that we saw in class. This is the fancy thing where we hit either the pit bear or a ball bearing with another ball bearing shot through a blowgun. Now in class I did this with this tilted at an angle. That's slightly more complex to analyze, but not that much more complex. So on the practice exam I gave you just the example where this is flat. Where we're projecting this ball bearing horizontally at the same time as we drop this one from rest, and we saw that they always collide right here. So part A is just a question of why they collide. And the answer really comes down to the independence of x and y coordinates. So if you imagine a straight path for the ball that has been launched, right? So if it were moving straight, it would move this way. But that's in the x direction. In the y direction, this ball accelerates downward at g. And how it moves in the y direction is totally independent from how it moves in the x direction. And well, this one only moves in the y direction, but critically it moves in the y direction in exactly the same way as this one. And because both of them will always have the same y coordinate at the same time, because they're both accelerating down at g, they both will always be at the same elevation. I can show this with equations also. So what I'm going to do is I'm going to choose this point where the red ball starts as my origin of coordinates. And I'm going to write down for the red ball its position velocity as a function, or excuse me, its x and y positions as a function of time. And I'm going to choose a coordinate system where downward is positive y here. So for the red ball, I have x of t is v naught t. All other terms are 0. That's very simple. And y of t is 1/2 gt squared. This is the distance I have fallen. This is the distance I have moved forward. All other terms are 0. But of course for this ball, x of t is just d, the distance, and y of t, the distance I have fallen, is 1/2 gt squared. So while they have different x coordinates, and it'll take some amount of time for this to wind up over there, the y coordinates are exactly the same. So I've explained in equations, right, why they always hit, because this is the same. Part B says, well, do this. We need to do the velocity too, so let's write that down. We don't need to do the velocity for the green ball. Let's do the velocity for the red ball. So Vx of t is just v naught, since ax is 0, and Vy of t is gt. There's no initial velocity in the y direction. Part C asks us how much time it takes for the red ball to fly over there and hit the green ball. So how much time does that take? We ask at what time does x of t equal d, question mark? Well, x of t is just v naught t, so v naught t equals d, t is d over v naught. We could have guessed this, right? We could have guessed that, well, the amount of time it takes is how far it has to go, divided by how fast it's going. How far has the other ball fallen? Well, both of them have the same y coordinate, right? That's the whole point. So I can just take the time I've got and plug it into that equation. What is y of t at this time? Well, y of t is 1/2 times g times d over v naught squared. So that could be written maybe more compactly as g d squared over 2 v naught squared. That's what we came here to find. Part E asks, how fast is the ball traveling when it strikes the other ball? Now, how fast is not asking about the y component, it's not asking about the x component, it's asking about the magnitude of the velocity. So part E asks, what is the magnitude of the velocity vector on impact? And of course, impact is this time. So the magnitude of v, which we can also write like this, is the square root of vx squared plus vy squared with the Pythagorean theorem. And here I just use the formulae I have, because I know how the velocity changes with time. Vy is gt, so it's going to be g times this. So that will be g squared d squared over v naught squared. And there's our result. Doesn't simplify any further than that. It's sometimes useful, though, to check units. So I'm looking for a velocity. It ought to be meters per second. Well, the square root of meters, excuse me, this is meters per second squared. Square root gives me meters per second. This has some funny units. So this numerator is going to be meters squared per seconds to the fourth times meters squared, all divided by meters squared per second squared. A lot of things cancel. This cancels with this. This partially cancels with that and gives me a 2. So this whole term here also has units meters squared per second squared. I take the square root and I get meters per second, so my units check out. So that's question 5 on the practice exam.